much William for such an extended period. It was great being here. It was great talking to everybody I talked with. This talk is going to be based on work that you've heard about some time ago, done with these two guys, and on the stuff that you haven't heard about yet, done also with those two guys. So anyway, before getting to that, there has been a lot of work about using field theory methods to help with the quest for precision as far as gravitational wave physics is concerned. And by and large, we are aiming to, us as a community are aiming to fill the 2 orders of magnitude gap in precision that separate us between now and the precision of upcoming experiments. So these 2 orders of magnitude include both instantaneous precision as well as accuracy that has to do with propagation of signals and propagation of errors over extended periods of time, such as hours, days, and months. So field theory has played an instrumental role in this quest, and there have been a lot of fast-paced results, many of which have been derived here. The red stuff has been derived here, and also there are some impressive results, somewhat off the chart at the bottom in the post-Newtonian expansion. And of course, there are equally impressive results involving spins and size. The reason I'm rushing over this is because this is really a very broad motivation, so it will have very little to do with what they're going to say. So now there is an important piece of input in this enterprise is the classical limit. And this is understood in the sense of force correspondence principle. Now, going through a little bit of algebra, this indicates that the momentum that's being transferred in any one scattering event should be much smaller than the momentum of the incoming particles. Now, we have to appreciate that this will be important later in the talk. We have to appreciate that this momentum transfer in any one scattering event, such as the one depicted there, is not actually the momentum that is being by which the momentum of an incoming particle is changed in the entire scattering process. This momentum transfer is really an avatar of that total impulse. And this total impulse can be constructed in a variety of ways. For example, by solving Hamilton's equations with the Hamiltonian constructism of scattering, which looks like that. Or it can be extracted from the atonal, which is really a resummation of these guys, of the involved infinite scattering. So now, throughout this talk, I will attempt to be as non-perturbative as possible. So I will not assume that Q is small, and I will more think of the S matrix as a resummation of this momentum transfer, which will eventually become the total impulse in a way that will perhaps hopefully be clear by the end. All right. So this is about, as the titles were saying, field theory for gravitational waves. Now, fortunately, the door swings both ways, and we could attempt to get information about field theory from gravitational waves. Now, we may not get as much information as we might want, but we might get prompts in which directions to look at. And this is part of the story today. But there have been actual, hard evidence that we should be able to learn from this. So, for example, this is a plot that shows how one might, the results that one might get by attempting to resum perturbation theory and reach the strong field's high angle scattering. So this currently perturbation theory is the solid lines that kind of end somewhere there, and the resummed version would go higher up. So ideally one should attempt to use this information to improve perturbative calculations, and get some kind of field theory summation that would produce the orange curve. Another indication in this direction is work of Mikhail and Dimitrios, who effectively told us how to compute certain whole-loop integrals by reading them off from classical physics. So perhaps we should attempt to get more of something like this. Now, a prompt that came out of studies of gravitational waves and comparison between field theory calculations and GR calculations, which for lack of a better picture, I showed as a graph, is that there is modes, gravitational modes with zero energy, and more generally mediator modes with zero energy, are important. And on the one hand, they're important, but on the one hand, they are difficult to get away with, but also they are kind of a pain in the neck to include explicitly. So the goal today is to somehow meander our way and weasel out of these subtleties and complications. And part of the issue is that, as David was rightfully emphasizing not too long ago, at the moment, the GR observables are not as well defined as they are in QC, as observables in QC. And basically, the reason has to do with the fact that there are no local observables in GR that one can actually trust. And at the same time, we are here and we are now, and we are making measurements here and now. Therefore, we have to somehow find a way to deal with this locality. So the next best things for observables in GR are scattering matrices, which are kind of non-local, but they're also kind of local. In ADS or DS, they are boundary correlators or cosmological correlators. And then there are also some kind of, there are also these final state expectation values of operators that are also QCD inspired. Now, these ones have some desirable features. All of them are gauge invariant in some sense. And also some of the inclusive ones, actually all the inclusive ones, like if it's operated as a momentum, all of the inclusive ones happen to be infrared safe. However, not all of them are infrared safe. And there are issues with that in the sense that the factorization of infrared divergences for those that aren't infrared safe has not been fully worked out. And also the local ones are not gauge invariant. And by local ones, I actually mean things that are computed this way. So imagine that here you want to measure a field, and you're measuring it here, but one of the transformations that one of the gauge transformations of GR is shifting coordinates. So the only way to deal with the equality of some local observables under shifts is to make it either integrate over X, which makes it non-local, or make it independent of X. And then, well, then it's a little bit too low. So this, waveforms, cosmological correlators, and so on, they all suffer from this because they're measured here. However, some things may fare a little bit better, such as the strain that's measured at LIGO. Because in some sense, this is non-local, and if you shift everything by the same amount, you measure the distance between 2 points. If you shift everything by the same amount, the distance stays roughly fixed. There are some corrections having to do with differences between the ends, but if the distance is not too large, then the corrections. So this one way to phrase this is that, and it's related to all the things that I said, is that it's not totally clear what is the origin of time. So if you shift the time, then this is changing the origin of time is one of these transformations. So one may wonder exactly what defines the origin of time, if there is such a thing, and if there isn't such a thing, then we have to figure out how to live with this kind of ambiguity. So anyway, to address some of these issues, one needs to understand why there is such a gauge ambiguity. Beyond saying, oh, GR is the diffeomorphism invariant theory, so we can change coordinates, end of story. And then two, we need to attempt to figure out how gauge transformations act on things that we might like to observe. So this brings me to kind of a plan. Morally, we are going to discuss the triality of concepts, large gauge transformations, 3-point amplitude, zero momentum, and coherent state dressings. So we're going to first talk a little bit about observables and what is the meaning of the word frame in this context, which I haven't quite defined yet, so bear with me for a little while. Then we are going to dive into something that has long been known, namely the definition of charged single particle states and how that is related to what I'm going to define as frame, and then 3-point amplitudes, and I'm going to be a little bit heretical and declare that they are not gauge invariant. Nobody cares to protest at the moment. Okay, and then anyway, we are also going to get to some consequences. In particular, we are going to invent some conservation laws, which are the PMS supertranslations, and then we are going to address a little bit of a puzzle about the frame or gauge independence of the total angular. All right. So to get there, we need to worry a little bit about observables and how we compute them. There are many ways to compute observables. For today, we're going to stick to this KMOC approach, in which they are constructed as differences of expectation values of some operators between initial, or rather final and initial state. And the final state is defined as the time evolution of the initial state. The time evolution happens to be done with the S matrix in the usual form, or in the N operator form, or semi-classically in the iconal form. And this operator can be pretty much anything. We are going to play a little bit with the angular momentum and the gravitational field. Here's the gravitational field in a form that I'm sure you have seen very many times. And then this expectation value has two pieces, an amplitude and something that resembles a cross section. Okay. Now, this is how we might want to do the calculations, but an essential ingredient in this calculation is what we mean by this initial state. And it has several components. A standard Fock space 2-particle state, which is really a tensor product of two 1-particle states. Something that defines an impact parameter, some wave packet that defines some relatively narrow things that correspond to these classical particles, and then there is an integration over phase space that sets these particles perpetually on shape. No. So that's that. So now one might wonder, this is the single particle state, this is the initial state. So one might wonder what exactly we might care to put in this initial state. Well, should we put any radiation? Well, at the moment, there is no radiation, right? There are no gravitons. This is the linearized graviton. We can declare that it sits at -infinity. It doesn't really know where it sits on its own. So if we compute this expectation value in the initial state, well, clearly it's zero. It's zero because this is just 2-particle matter state. So Fock space algebra says there is nothing there. Now that's a little bit odd. Right, so that's a little bit odd because if you take any old particle, my phone, not particle, it has some field at infinity, which looks very much like a linearized Schwarzschild. If it stands still, if it moves, then it's boosted linearized Schwarzschild. So one might wonder, why exactly isn't it there? Should we put it or should we not put it? Well, as it turns out, this field actually does come about in the KMOC formalism with this initial state, except it doesn't come about from the initial state. It appears from interactions. Right, there's a piece that comes from here. The piece that comes from, I guess, here, that produces it in the final state. But it's not there in the initial state. Right? As it turns out, if you look at it, this is literally just a normal 3-point amplitude. So not only that, but it's really the 3-point amplitude with real momenta. And it has to be real momenta because we very much like our metrics to be real. So if we take a 3-point amplitude and force its momenta to be real with everything on shell, then it has only one support point in phase space, which says that the graviton is, or rather whatever mediator that is, that has to have exactly 0 in. So is this something that we should worry about and keep it as such, or no? Well, it's certainly there if one computes the waveform. So somehow the only way to make everything here consistent is to expect that there is some kind of freedom where this thing is assigned. It can be assigned to the initial state, it can be assigned to the final state. The only way to have such a freedom is to somehow this be in fact dependent on gauge. Which gauge that is? Well, surely it cannot be any old gauge transformation, because this is invariant under normal gauge transformations. Epsilon goes to k will certainly kill this. P square is on shell and k square is 0 because of that. So it has to be something else. But it has to still be some kind of a gauge. Okay, I should say, feel free to interrupt. I tend to go on for two. Okay, so now how can this be? How can this be? Right? We have a normal 3-point amplitude. How can this be a gauge? Well, so here's an example. Consider a static Coulomb charge. This is its vector potential. Clearly, it's got nothing at infinity. So the physical components of this would be the transverse traceless pieces, so things that live in the angular directions on the celestial sphere. So clearly, it's got nothing in there. This is just a dt. Now, imagine for a second that we take this and boost it to some momentum or some velocity v. This is the field, and then there is something in the angular directions. And if you do a little bit of algebra, or you ask Codex to do a little bit of algebra for you, and ask it to split it up in this form, then you quickly notice that the angular directions are this. They are total derivatives, so they are in fact the gauge transform. What does this mean? It means that if we this field is literally also the current created by this moving particle. So what this means is, and I should also add that current is actually the 3-point amplitude, matter, graviton, except except that everything is on shell. So this is an illustration of what I meant. We have a 3-point amplitude, which is given by this, and happens to also be a gauge transform. And not only that, but this is also not any old gauge transformation. It's not a gauge transformation. It's a gauge transformation that does not fall off at infinity. It has no radial dependence. It only has angular dependence. It is, of course, in QED, when we express everything in terms of field strengths, this is, of course, 0. It means nothing. But if we were to somehow need to worry about the vector potential itself, then it would contribute no field. Okay. So now the same happens to be true in GR. I'm going to skip the details, and I'm going to save your tolerance for long derivations for later. But in GR, the place where the way to expose the radiative degrees of freedom is usually in the bonding gauge and bonding coordinates. This is their definition. As it said, these are the gauge conditions, and the solution to this gauge condition is a ds square of this form. And if one further assumes certain fall-off of these coefficients here, in particular that the spacetime becomes Minkowski at infinity, then everything is determined by a single tensor in vacuum. The single tensor, this is CAB, which goes by the name of shear, and it is the 1/r correction to the sphere, to the metric on the two sphere. This happens to also determine the psi4 Newman-Barrow scalar, which is why this captures all the radiative. So in this gauge/coordinates, the linear Schwarzschild metric looks like this. If you squint at it a little bit, I'm sure you can recognize a couple of things. You can recognize the polarization tensor is EB. And you can also recognize the P nu, the usual P nu, which is the stress tensor of flow. Now, this gauge exhibits a collection of remnant diffeomorphisms that preserve this gauge. And these diffeomorphisms change this the shear in this way, while also shifting the time. So in particular, one could very well take this and set it to 0 by such a gauge transformation. And therefore, while there is a stress tensor, the radiative part of that stress tensor, the contribution of the radiative part of that stress tensor to the on-shell 3-point amplitude happens to be 0 in this particular gauge. in which we choose to apply the ferromorphism to set CAD. So there are three conclusions here. The initial state particles can have some time-independent Coulomb field. This would be omega equals 0. There is a duality between asymptotic radiative fields in this sense and 3-point amplitude supported on exactly 0 frequencies. And both of them can be changed simultaneously by large gauge transformations. I should stress this is also a large gauge transformation because this depends only on the angles, it doesn't involve. So it's time for me to define the word frame. And the frame is whatever profile of zero energy gravitons in this case we decide to add to the initial state. So in this sense, the frame and the value of the on-shell 3-point amplitude with zero momenta are almost similar. Okay. So this said, there are two perspectives on 3-point amplitude with zero momenta. One of them is that they're there. They're supported by they're supported at omega equals 0, and they correspond to a Cheryshev frame. The old work with Saad and with Donald said that indicates that they can be resummed, at least in one particular instance that we analyze there, and they can still be resummed in general. Another perspective is that we can always choose the 3-point amplitude with real momenta to vanish, and then we can add them back a posteriori by a gauge transformation. So to actually carry out this last step, we need to figure out exactly how those gauge transformations act on pretty much everything else. Okay. So now there's an interesting digression here. So I argued here that there is a gauge in which the shear is 0. One might wonder, is there, what's the actual Schwarzschild metric in that gauge? Is there anything interesting? Because if it's interesting, then we might consider using it for something. Let's see. Anybody has a guess? The people who thought about amplitudes for a while, they might have a guess. Anyway, here's the answer. It's the Schwarzschild metric in Kerr-Schild coordinates. So this is the Schwarzschild metric in Kerr-Schild coordinates. Is extremely simple. Also a solution to linearize Einstein's equations. So one might think that it should be easy to track, and indeed it is. So one takes this and puts it in Bondi gauge, then this is the expression. This is Minkowski space, and the correction is only in the retarded times square direction. It's got nothing correcting the metric on the sphere, so the shear is empty. Now, of course, one could attempt to construct the usual the deformers that connects this to the usual shear in Schwarzschild coordinates, and this has been done. It looks like that. This is something that appeared on the slide before. There's something that's a little bit worse. There's a logarithmic log R dependence. So in fact, this blows up at large distances. There's a reason for it. This has to do with infrared divergences from a scattering amplitude point of view. That's really a story for another talk. So that's it. All right. So getting back to these this duality or this relation, this key perspective on amplitudes. So should we worry about any of this in the first place? Should we worry about these gauge transformations? Well, in QED, certainly we shouldn't. In QED, with sufficient effort, everything can be expressed in terms of field strengths. These gauge transformations do not affect the field strength, so we don't really need to worry too much about it. In GR, however, the story is a little bit different, because even if we were to express everything in terms of the Riemann tensor, which is the analog of F here.
What about Yang-Mills theory?
In Yang-Mills theory, we don't measure gluons, so we are safe from that perspective. But yes, in Yang-Mills theory, we should at least consider the possibility that they might actually be.
You can measure the gluons in real QCD limits. You add 50 quarks and the theory of infrared rate. It's probably the same as GR already.
Okay, then we should worry about it.
Yeah. All right.
And in fact, this is this is a comment for the last slide of the talk, but in principle, we could in QED, if we were to measure QED, if we were to measure photons, then we could in principle measure what these 3-point amplitudes are by essentially measuring, having a 4-pi coverage of the event. Unfortunately, we can't have that in GR, but that's interesting. Right. Okay. So now this is not invariant. It's not invariant because it's not. Arminian is invariant under the bit of the thermostat that changes the shear by itself, but it's not invariant on the shift of the retardant. It's really this thing that messes it. So this brings us to the remaining questions. Is there a right frame? And this is what I was meaning earlier, that one could measure it. One could measure in the 4-pi coverage. This is the frame, whatever that may be. And also we need to figure out how to adjust the frame in an on-shell setting. But before getting to these questions, one might wonder if what I'm saying here causes a revolution. Apparently, everybody's clear that it doesn't, because nobody shouted at me. Anyway, let me address that question about the revolution. And that goes back half a century or so. Basically, the reason this might in fact seem like a revolution is that I'm saying that 3-point amplitudes are ambiguous. And most of the time we are very happy with saying, no, they surely are not. In fact, it's been known for quite a while that in some sense they are ambiguous, but they're not ambiguous as vertices. They are ambiguous because of what we call asymptotic states. So that's where the ambiguity is coming. So the idea is that the properties of asymptotic states have been characterized at some level by Schlein and Lehmann, like I said, about half a century ago, and it's all captured by the spectral density in this representation of the 2-point function. So in gap theories, this the spectral density has a very distinct structure. It has a localized delta function width, and then a continuum later on. Of course, it could happen that accidentally these are in the same place, but this delta function still survives. So this isolated pole is something that we love very much. We teach students that renormalization, on-shell renormalization scheme relies on it, and it does. Now, as one goes to gapless theories, the story changes. This isolated pole disappears, or rather merges with that, with a continuum, and it stops being the pole altogether, in fact. And the spectral density looks like this. It has a cut starting at the Lagrangian with the bare mass. And then not only that, but the cut has this is not a rational exponent. This delta depends on the coupling, and not only that, but also happens to be gauge dependent. So this is result from these two people in late 60s, early 70s. Anyway, so no, we're not causing a revolution. This has been known. The fact that there's an ambiguity in the definition of single particle states in theories with massless mediators is essentially captured by this. And morally, this gauge freedom that I was describing earlier is reflected here by the gauge dependence. So one could be even bolder and say that not only they're ambiguous, but they actually depend on the history of the state. And I'm happy to elaborate on this, but not right now because I'm here.
That's because they're two very different phenomena. One is just mathlessness, even without any gauge, any mention you take any kind of theory of scalars and fermions, especially in lower dimensions that, for example, make a conformal field theory. And in the conformal field theory, there are no single particle states, just because of scaling and when things behave in infinity. But everything is gauged. And nevertheless, there are no single particles there.
Well,
and on top of that, in QED or whatever, you would have things that are not gauged there.
Yeah, but this is, I think this is different from that. This is basically a reflection of the fact that you can add there's an arbitrary amount of zero energy stuff that you can add to any massive stuff without changing it, without effectively changing its momentum, effectively changing its mass.
It's probably true in any gapless theory, that's just kinematics. If you have a density of states that goes all the way to zero, you just put very,
Yeah.
spread it out very thinly and then you can arbitrarily a lot of stuff.
Yeah.
But that doesn't, that's still totally gauge invariant, that does nothing. In those cases, for example, you wouldn't have these gauge dependent exponents. And there would not be any large gauge transformations.
Well, I'm not sure I can comment in any meaningful way about this, though I will come back to it later in some sense. So there will be a calculation that I'm going to describe that that addresses some of these, tells us how to move between various frames. And while we understand what they actually mean for GR and at some level also for QED, the calculation goes through also for mass in the presence of massive scalars. And it will still capture some kind of freedom of exactly this type, while not being very clear what it actually means physically. So I should add here, or of course, this is gauge dependent in QED. I don't know what, in what sense this could possibly be gauge dependent in just a mass theory with massive scalars. Well, there is no gauge there. But begin with.
So it's not like field redefinition, like ambiguity stack.
There's a physical spectrum there.
But here you're correlating sort of with a gauge dependent correlator, right? This charge function. So you can consider a gauge invariant one function. Sure.
Well, that's of course a very fair point. Green's functions are never quite gauge invariant on their own, but somehow this still feels worse because we know how scalars transform under gauge transformations. So if one were to look at the scalar, we know how scalar transforms under gauge transformation. It doesn't quite affect this one directly. But perhaps there is a relation. Perhaps there is a relation. Right. So anyway, getting back to how to include these. So the idea would be to start with these Fock single particle states and dress them in this sense with some with some cloud of massless stuff. But of course, there is some amount of constraints that we need to put in. For example, we need to make sure that the momentum of the particle doesn't change or that the normalization of the state doesn't change. So between these two, there is really only one solution, that there is a phase that gets to dress this initial particle. And then if we also want a nice classical limit, then this phase has to be, in fact, a coherent state. Now why exactly, where in here comes the idea that everything should be localized on zero frequency states? Well, the idea is that for a particle that just sits still, its field has to be time independent, and time independent in momentum space translates into zero frequency. Now, I should stress that this is certainly this is an idealization. Everything that I said here, localization, time independent, so on and so on, exists is true only at strict asymptotic infinity. If you put something that's charged in the middle of the space and you potentially have something that's charged at some large but finite distance, then the thing is not going to be time independent. The particle will start moving. So this delta of omega will need to somehow capture a little bit of width because of the presence of other things that act on this particle that exists elsewhere in the plane. Anyway, so for the time being, I'm going to just assume that this particle is totally isolated, sits at infinity, and so on. And because otherwise, we're not going to finish today. Okay, there is an analogous idealization that enters in the calculation of the operator that captures the metric at infinity, its strict asymptotic infinity. The calculation involves a saddle point approximation that assumes that the frequency times the observer distance is much larger than 1. Now, this might seem like a reasonable approximation because any event that we might ever see is out there in the universe, millions of light years away, perhaps. However, as it turns out, in this idealization in which we are allowed to wait infinite amounts of time, then there is such thing as gravitational wave memory. And the gravitational wave memory just is a time-independent difference between initial metric and the final metric, which is localized, therefore, on zero frequency gravitons. So if we, in that same idealization, we are forced to consider modes that have exactly zero frequency, and they would seem to violate this. So the way to go around this, at least temporarily, is that we are going to introduce some kind of hierarchy of scales. And this observer distance is going to be assumed to be extremely large, much larger than whatever other scales there are in the problem. And then the limit is taken. First, this goes to infinity, and then omega is sent to zero. Okay, so now dressing. And how we get this Coulomb field out of dressing. So there is this phase that we're going to state by. Then if we just compute the expectation value of the operator that I just defined for you, it's very simple. It picks up the same 1 over R that used to be here. So, and this will just, its expectation value is easy to compute in a coherent state. And then we find that everything, that the Coulomb field is literally determined by this shape function here. Now, because this shape function multiplies the graviton creation operator, it should have, and here is an index that is the helicity of that state created by that operator. It should be a spin-2 function. And the spin-2 function generically can be written as a second derivative of a scalar function multiplied by a polarization tensor. So another way of phrasing this is, of writing this is as this operator on the 2 sphere. So if you remember, I don't know, 5 or 6 slides before, this is exactly the kind of transformation that we're shifting the sheet. Now, an example of this is the so-called Veneziano-Vilkovitzky supertranslation, which also appeared on that same slide, which looked like that. So if you take this and plug it in there and you crank through, this is what comes out, which is the regular 3-point amplitude in, written in these finite coordinates in the celestial sea. So now this said, it just follows that such a coherent state dressing can generate any Coulomb field from nothing. So it can be used to map any state to any other state in any other field. So now we can generate the field, the Coulomb field. The one thing that this doesn't generate on its own is a shift of time, because this doesn't happen anything, it's just that. So the next story will be to worry about the shift of time. But before then, a little bit of a summary, which is basically everything that I just said. There is one thing that I would like to emphasize here. This operator, as it's in fact a projector at some level, it projects out the modes with L equals 0 and L equals 1 out of this gauge parameter. And this is related to something that was observed not too long ago by Bibi, Danur, and Geralico in their comparison of GR derivations of waveforms and field theory derivations of waveforms at this relatively high Tn order. They found that it is necessary to reach into this Veneziano-Vilkovitzky supertranslation and remove these modes. And they conjecture that such a removal is necessary for loop orders. Well, this little derivation here indicates that their conjecture is in fact correct. It is this kind of transformation will always remove those modes for any loop order.
These are not the normal translations.
Normal translations.
Okay.
No, they aren't. I don't remember exactly why, but these are.
The normal ones don't blow up.
So
Not worth my time.
yeah, these are also, these are, yeah, I don't know. Let me think about this. There is a good answer, I just don't know. All right, anyway, so this is half the story. Now, what we want to compute for as far as observables are concerned is things like these. So the idea would be to try to look for an operator Q H such that QH commutes with QS, and then we can take this combination and push it past the S matrix. So then we let it act on the observable, and then we'll need to worry about the remainder later on. So we will try to compute QH out of by looking at the commutator of QS with the S matrix. So this is the calculation is somewhat similar, at least in spirit, with the one that I described 2 years ago or so, the year and a half. So I'm sure everybody remembers the details of that. Anyway, the idea is that this commutator, or rather this conjugation, is governed by this particular commutator, S with QS. Now, in principle, it's governed also by the nested commutator of that with everybody else. If we are bold and hope that in fact this combination actually commutes with the S matrix, then we need to worry only about this, and we'll see that that in fact is a reasonable hope. So QS is what I wrote before, and because it's linear in creation or in creation operators, it talks individually to all the external gravitons of the S matrix, and because it's localized on zero frequency, it wants those gravitons to be in the soft limit. So in that limit, and in fact, it's the leading soft limit just because this is nominally identical. So these are the S matrix elements for when this graviton is attached to an incoming or outgoing particle. In the soft limit, this curly A is the soft factor. This is the propagator that connects that soft factor with the rest of the amplitude, and H is the hard part of the amplitude, which is going to just tackle. So we want to compute this commutator, and this commutator comes out of comes in five pieces. Here in these pictures, the red dot is the stuff that comes from the dressing, and the green triangle is the stuff that comes from the soft factor. So that soft factors can be attached to a graviton or to some other matter particle. And the relevant integrals that need to be computed are these. Where F is arbitrary, is the thing that comes from the dressing, the delta function is from there, and K is the soft factor. So interestingly enough, we are going to compute these integrals for arbitrary dressing. Okay. So here is the first bit when this graviton is connected to a soft factor attached to an external gluon. So this is the dressing part. This is the soft factor, which, as always, it looks like a stress tensor. And then in here there is a projector, a transverse faces projector, which is made up from just summing over helicities of two polarization tensors. Now, as it turns out, this integral is just that. It's for arbitrary t. The way the calculation is not entirely straightforward. There are two kinds of singularities that one needs to worry about. Singularities at omega equals 0, and there are also singularities when k dot L is 0 because without omega being 0. And that could happen because k is a graviton, so it's light-like. L is on shell, therefore it's light-like, so they could be orthogonal. So anyway, and because so one needs a special regularization, different regularization for the two singularities. Long story short, this is the answer with a projection on L larger than 2 being enforced by the solver, just in case. So now there is an operator that, when commuted with a hard part of the S matrix, produces exactly that, and it's this one, proportional to another operator for gravitons. And this individual dressing factor QH for this number operator is just this. Okay. So now we have this. Therefore, we can answer immediately the question, where does this shift in time come from? From here. So this is just to recall, this is the gravitational operator at infinity. The retarded time appears over here. If we conjugate this operator by what I said earlier, QS plus QH, then QS is going to produce the Coulomb field in whatever frame we are, and then QH is going to act as the number operator on this, going to produce a single factor of T for each of the external guys, and omega K is omega K. This should have been a capital filter. So combining these two, omega is common between the two, so this thing just shifts the retarded time, and this is exactly what the gauge transformation instructed us that we should do. All right. So now, what about the rest? The rest of the four pieces. The rest of the four pieces are integrals that are easier to compute, though the results are slightly more unpleasant because there are some leftover integrals that cannot be computed exactly without assuming something about these. Nevertheless, there is another addition. There's another Q that can be constructed which can fill these guys, and it looks very much like these, where these I's and J's there. So all in all, there is a completion of QS to something that commutes with the S matrix, and for any decimal factor. So this is I should say this calculation was done with for gravitons. There's an analogous one to be done for vectors, and there is something identical that can be done for scalars. For scalars there is no such projection. For vectors there is one, just it kills the zero mode. And this is what I meant earlier, that everything that I'm saying goes through for scalars, even though I don't actually know what that object is. It's a symmetry that lives at infinity. It's an asymptotic symmetry. I just don't know what it is. Okay, so now this is so we have gauge transformations and gauge. We know how things. We have operators that act on supposedly observables. Now let's see more of that, and get to the last bit of the talk, which is the resolution of a little puzzle about the angular momentum. So we have QS and QH. We can combine them in this way because even though I didn't stress it, QS and QH actually commute with each other. So now if we take this observable to be an inclusive one, which one might expect to be independent of gauge and infrared safe and so on, then one finds an interesting thing that was, at least this part is known quite a while. So if one takes this to be just the radiated angular momentum, then these objects act on the creation of the graviton creation operators in the radiated angular momentum, and they shift it by a constant. Well, it's not only a constant, so it's a constant that depends on the momentum. And this thing, when it's plugged back in there, it produces an order G square emission in the angular momentum, which was first pointed out by Damore, which is a puzzle for some. The puzzle was ultimately resolved at some level by Choshen and company, and also privately by Michaels and Enrico, I guess, and Julio. Is there anybody else? We don't forget it. Anyway, maybe Mao. Anyway, so yeah. Now, the conclusion of this little thing is that the radiated angular momentum depends on the frame. Right? We have this QS that defines for us a frame, so the amount of radiated angular momentum depends on the frame. Now, the total angular momentum is something that's perhaps its conservation we hold a little bit more sacred than the conservation of the radiated angular momentum. So one might wonder if that one is also frame dependent. And the other question that one might ask is, what's up with this fellow that we left behind? Right, so we had QS in the dressing, we added and subtracted QH, half of it went away, and there was something left behind. No operator has to be left behind, so we need to deal with it. So to actually figure out what's the purpose in life of this fellow is we need to understand a little bit better what is the final state obtained by evolving such an initial state with QH acting on the Fock state. So this is unlike QS, which was creating infinitely many gravitons of zero energy, and it was not an eigenfunction of anything useful. This one, the Fock state happens to be an eigenstate of QH. So in fact, QH here, because QH is just a collection of non-products. So this QH, in fact, could be replaced by just a function. Not really. So we can understand a little bit better what this object is. And the calculation is following quite closely a calculation that Matteo Donald and company did some time ago. And because the time is running short, and the patience is presumably wearing thin, I am not going to appeal to your tolerance for long calculations. But the short version is that the way to compute this is to project it onto a complete set of final states and then evaluate these matrix elements by saddle point approximation. So once you do this, what you get is the following. So saddle point approximation involves using an iconal representation for the S matrix. So the iconal representation for the S matrix depends on some parameter that's integrated over, here called X. And Q is this momentum transfer that was a little bit nebulous early on. It's the one that I wanted to keep exact. So I did keep it exact in the image that I showed you. Anyway, so this X is the this X is an integration variable evaluation. So the conclusion of this saddle point approximation is that the momentum transfer at the saddle point is the impulse and is given by the derivative of the iconal with respect to X. This is a standard thing that has always been true. Now, there is a non-trivial relation between this integration variable X and the impact parameter defined at infinity, which looks like this. Alpha and beta are defined by orthogonality. So if you cross out the last term, this is something that has been known before. This is the usual relation between the impact parameter at infinity and the so-called iconal impact parameter. And that relation gets corrected by something that depends on this hard charge that is set. So in this point, it's perhaps not clear that what the relation is between X and B, but as far as norms are concerned, perhaps it's a lot more recognizable. And then in addition to this, there's a lot of garbage that involves this QH and its derivatives evaluated at the value of for QH equals the impulse. So this was the reason why I didn't want to expand in QH. QH is the impulse. The impulse doesn't need to be small. It's not, it doesn't measure, it doesn't count quantum effects in any sense. It is something. One could attempt to expand it in G, but then the expansion of this guy in G is going to mix with the expansion of any other observer. All right, so where does this take us? So this takes us here. So let's look at, if you wish, the leading term, linear in the impulse. And this is the iconal stuff. This is the new addition. So if you rewrite this in terms of the impact parameter, then it turns out that it shifts the mechanical angular momentum from P times B to P times delta, with P times delta B, or delta B is this. And as it turns out, this addition cancels exactly, at least in the case of this particular frame, cancels exactly the radiated angular momentum. So at least in QED, this restores order. The total angular momentum is frame independent, but that frame independence comes as a frame dependence of the mechanical angular momentum and of the radiated. And the same happens in GL. things are interesting enough, not a lot more complicated in GR than they are in QED, at least not of this order. I should say this is the fact that this balance actually occurs has been observed long ago, or maybe not that long ago, 5 years ago or so, in QED here and in GR there. Of course, we could potentially compute the next order corrections because this expression is exact and QH is exact, and we know the impulse is at substantially higher orders. While we don't know the radiated angular momentum to higher orders, we could in principle compute its frame dependence to higher orders. Basically because it's not that complicated, it's just this stuff. But all right, so this brings me to the last 3 minutes of my time here and the last few slides of my talk. So I filled your ears for the last hour or so with 3 stories about zero energy mediators, Coulomb fields, asymptotic charge particle data, and S matrix elements with delta function support. And I hope I convinced you that they are very much related to each other. 3-point amplitudes with real momenta and on shell are frame dependent. They capture the long distance field of a particle, which can be changed by coherent state dressing. Every coherent state dressing can be extended to a conservation law. And then one piece of this produces a shift in the retarded time, and the other shifts the impact parameter. Now, we use this for the angular momentum, but a shift in impact parameter happens everywhere, including in the impulse, including in the scattering. So one might need to worry a little bit about what that field is. And we can talk about that later. Now, I also discussed that a little bit. There are 2 caveats that I would like to bring up here. So everything that I said relied at some level on being strictly on zero energy modes, and the fact that the detectors are placed at strict null infinity. It would be potentially interesting to relax this, though not straightforward to do. The other thing is that in the derivation of the impact parameter shift, we use the Econo form of the S matrix. Now, clearly that assumes that it's an elastic scattering, does not produce additional radiation in the final step. One could attempt to relax this by promoting the Econo to the full N operator, but that's also the story for another time. However, yeah. So last but not least, here are a collection of questions. In particular, one that has perpetually entered in various discussions is the supertranslation frame observable? And as we were discussing a little bit earlier, in QED it might, because one has 4π coverage. In GR, probably not, because we measure the single point, and this translation of the retarded time by in an angle-dependent fashion reduces to a single constant. Whereas in QED, if you have coverage to an entire 4π or even just 2 points, one would be able to observe the angle dependency. Now, something that I was expecting that somebody would shout at me earlier, but nobody did, is what's the connection to Fadeev-Kulish dressing, which has a similar flavor. Well,
actually, sorry, the previous one. So the pulsar timing arrays, why not? Can't you do something with that?
I don't know how the pulsar timing works. One would need to know when the signal was emitted in order to be able to tell, in order to be able to discern this. So there's another option which doesn't rely on that, but it relies on a statistics kind of approach. Right? So if you have here's an event and 100 detectors around, this is morally equivalent to 1 detector and 100 events around. But the problem with this statistical measurement is that we don't know when the signal was emitted between the various events. So and for each event, this is just a constant shift. So that's I would think that for the pulsar timing is a similar problem, but I'm not sure. Yeah, so getting back to Fadeev-Kulish states, which are again some kind of coherent state dressing of charged particles, they have been, their purpose was to define IR finite scattering. Our purpose was certainly not that. And in fact, the dressing that addresses, for example, the Veneziano-Vilkovitsky supertranslation is not anything nice as far as addressing the IR divergences. Besides, for these observables like the waveform, there are additional IR divergences which are not cured by this dressing. So there is no real reason to talk about these kind of states in the time context. Now, many of the other things here that I already mentioned, like I will not know what this means for scalars, even though there is a conservation law. Finite distance is interesting and difficult. There's another little story about infrared divergences and our ability to use the body coordinates to separate the radiated degrees of freedom. But that is also an equally complicated story and a longer story. So anyway, to wrap up, we got into this story by being prodded by comparison between quantum field theory and GR. We were prodded in that direction from the GR point of view. And I do believe that there is a lot more to learn about QFT with inspiration and comes from classical G. Thank you.
Any more questions for Radu? Everybody's happy.
Everybody's asleep. Everybody.
One of the two, but in any case where just wait a half hour or go to your office, come back in a half hour. We're having a little reception. We're gonna Thomas winning at the prize, the new Rises prize. And then I need a couple graduate students who are strong. Bring the coffee in here. It's in the it's just next door.